This is video 11 in the lecture on the design of reinforced beams, and it's in the group of ultimate limit state. At the end of this section, you will be able to calculate the needed tension reinforcement in domain 1B simple bending. We are now in the chapter of simple bending for rectangular cross sections, and we are going to see what the formulas will be in domain 1B. Consider a strain diagram unloaded, and on the x-axis it's the strain in the tension reinforcement. This is the total height of the section. This here is the strain in the concrete. We have the maximum strain in the steel epsilon UD, and we have the maximum strain in the concrete for the parabolic part is epsilon C2, and for the plastic part or plastic behavior, or it's the epsilon CU2. The effective depth is D. Now for pure tension we have this strain diagram, and when we are considering now domain 1, which is this portion here, this is domain 1. The right border is when the strain in the steel is maximum together with the strain in the concrete. This part, or this domain 1, can in fact be subdivided into 3 different parts. Mainly it's 2, it's domain 1A and 1B, but 1B can be split up in 2 other regions. Just to make it clear, this is the strain and this is the stress of the concrete. You see first you have the parabolic part until epsilon C2, and then the rectangular part up till epsilon CU2. Now this first part we call it domain 1A, and then the part next to it is domain 1B. This part is 1B, this is 1A. But 1B, we can split it into 2 separate regions, one with the parabolic behavior and the other with the rectangular behavior. Consider a cross section, then we can see what the strain diagrams mean. After that we have the stress diagram. You notice that in domain 1B you only have a parabolic diagram. And then we have the actual forces at the end. In domain 1B, the pivot point is epsilon UD. It's the strain, the maximum strain in the reinforcement. And we have taken this as 10 per mil. So this is the fixed point. We don't know the epsilon C, the strain in the concrete. Now, through the stress-strain relationship of concrete that we saw in lesson 1, the filling coefficient and the center of gravity we will derive by integration. So if you take in domain 1B, we know epsilon S is 10 per mil, and epsilon C is between 0 and epsilon Cu, or epsilon C2, which is 2 per mil. So this is the parabolic area. The 2 is only valid for concrete grade smaller than C50. This is the strain diagram, 10 per mil, and then epsilon C somewhere here. This is the neutral axis. The depth of the neutral axis is X, and these are the stresses. The coordinate starts with S, 0 until S equals X. The integration of this parabola or piece of parabola is the concrete compressive force Fc, if you multiply it by the width of the section, of course. And the position of the component Fc is delta Gx. You can describe the strain in the concrete as a function of S, and then you have this relationship. For S equals X, you see immediately that we have the rule of similar triangles. The total compressive force in the concrete is equal to, of course, the filling coefficient times the width times the depth of the neutral axis times the compressive design force, and this is equal to the integral of the stresses in the concrete going from 0 to X. If we do that, we make those two equal, and we regroup according to the filling coefficient psi, then you will see that psi now is a function of xi, and xi is the depth of the neutral axis. It's x over d. Remember that in the domain 2a, psi was independent of xi. Now we have a dependence rule, which is this one. We will calculate the position of the location of the force Fc, of the compressive force of the concrete. We take the rotation equilibrium according to the neutral axis, and it is the same. It is this bending moment equals the integral of S sigma c ds from 0 to x. And if we work this out, we find that delta G is also a function of the position of the neutral axis. Now in table 1, you will see the first portion. This is domain 1A, but it's 1A and the first part where only the parabola is used, where the parabolic relationship is used. You can see here epsilon s, it's 10 promille. That's right, because that was a pivot point, and epsilon c goes from 0 to 2 promille. That is the region that we are studying at this moment. So it's about this portion of the table. And the two relationships of psi and delta G, you see that this is varying according to xi x over d. Now, for this region 1b, the first part of this region 1b, the left border is xi is 0. That's obvious because there's no compression zone, and then mu d, the reduced bending moment, is also 0. On the right hand side, we have xi equals to 0.167. We have seen that already because it's the same. No, it's not the same. We will see it just now. And mu d, the reduced bending moment, is 0.104. We will just see it now, right now. The psi and the delta G, we have we can calculate it. We have seen the formulas because psi and delta G is a function of xi, and xi is 0.167. So psi and delta G has for this right-hand side border a fixed value. So we are in the region where the strain in the concrete is smaller than 2 promille, but that's only for C50, for qualities smaller than C50. In fact, it should be stated here instead of 2 promille, it should be stated epsilon C2. Then, as a summary, rotation equilibrium for around the tension reinforcement gives you this formula. The translation equilibrium gives you this formula. And to calculate the reinforcement, you can use this by zeta, or you can use the omega. Now, the right border side of domain 1b, when epsilon c is smaller than epsilon c2, or it's smaller than 2 promille, that's this line. This is 2 promille, this is 10. So now if you look at this picture, it's easy. You see that xi, or x over d, is just the rule of the similar triangles. It's always the smallest two divided by the sum of the two. It's 1/6 or 0.167. That's C, the position of the neutral axis. Delta G, we have done by iteration, we have derived this formula. You fill in the Xi and you have 3/8. And the Psi is the same thing. We have seen the formula. You fill in the Xi and you find Psi equals 2/3. So that's for the right hand side of that domain. And then we can calculate mu d, and mu d is 0.104. And the zeta is 1 min delta g Xi is 0.9375. So if you have a section of a concrete beam and you have a bending moment and you have to calculate the reinforcement, you start always with calculating mu d. Why? Because you want to know in which domain is this situated. And if the mu d is smaller than 0.104, then you are sure you are in area 1b. And then you can apply this formula to calculate the reinforcement. Now we look at the other part of domain 1b, where the strain of the concrete is between 2 and 3.5 per mil, or where the strain in the concrete is between epsilon C2 and epsilon CU2. Then we have the diagrams of the strain and the diagram of the stresses. You see now that we have the parabolic rectangular stresses. And we have the strain of the concrete in function of the coordinate S. Now we can do exactly the same what we done before. We calculate the total compressive force as an integral, and we find that Psi, the filling coefficient, is again a function of Xi, which gives you the position of the neutral axis. Xi is x over d. And then for the rotational equilibrium, we do again exactly the same, and we find that the position of the force Fc, the location of the force Fc, is also a function of Xi. Then all those values are calculated in table 1 for ease of use. If we now look at this domain 1b, the second portion, when epsilon c is between epsilon c2 and epsilon cu2, then we have seen that the left border is those values are valid for the left border, and with mu d 0.105, and the right border of this region is of course the region that we have already seen, because this is the left border of domain 2a, so with those values, and mu d equals to 0.187. Then for the formulas, they are the same. Rotation equilibrium gives you this formula, translation equilibrium this, and the reinforcement is given by this formula. You can now calculate the needed reinforcement of a beam with a maximum strain in the tension reinforcement.